Hey guys, I'm going to run you through this handout very quickly, and I know we've covered parts of it in class, but since I'm making a video, I might as well just go through the whole thing, right? I think so. So, let's have a look. First problem, 2.47. A ball is dropped from rest above a hard floor. When it reaches a floor, it has a velocity of 4 millimeters per second, and then the ball bounces vertically upward. Okay, so figure 2.77 shows a graph of the velocity, and the positive for direction for velocity is upward, which is actually slightly confusing, and I'm inclined to think is a mistake. In any case, let's take a look at our graph because we need some information here to set it up. First, these purple lines, squiggly lines, show that we're not actually interested in that initial velocity. Okay, so this point is not important. Likewise, over here, our change in velocity down here, also not important. What is important is the red line that I have left in terms of momentum. So this point shows our initial point of impact. So this is the time at which our collision with the floor occurs. And this point down here shows the moment when the ball ceases its collision. Okay, so during this period, the ball is compressing, it's deforming, it's basically bouncing. And I may try to find a video, a slow motion video of that occurring because it's cool. Okay, so what we gain from the graph is the information that we have a velocity of 4 meters per second at the part of the collision we're interested, the start, and we have a velocity of negative 2 meters per second at the finish of the collision. Okay, so we can express that as I have shown here. Note that our second velocity is in the opposite direction, so we affix a very important negative sign. Okay, and do not neglect to do that because this is the point where negative signs become very important. So I'm going to change that to purple. There. Now you know it's important because it's purple. Okay. So we can also express our momentum in terms of those velocities. And to do that, we use the same subscript. So I have here a v sub 0, which is an initial velocity at the start of the collision, and v sub 1, which is the final velocity at the end of the collision. So you can call them whatever you want, but I've chosen the subscripts 0 and 1. And for my momentums, my subscripts correspond, which is just a rational way to do things. Okay, so we have here initial momentum at the beginning of the collision and final momentum at the end of the collision. Okay, what we're interested in here to find the magnitude of momentum change is, of course, a change in momentum. And that always involves the final thing minus the initial thing. And so that looks like momentum sub 1 minus momentum sub 0. Okay. And we then substitute the values for mass and velocity. And in the next step, we factor out mass because we don't like typing the same thing into calculators repeatedly. You don't actually have to do this step. And then last, we substitute our actual values. So we have here 0.5 kilograms times the quantity negative 2 meters per second minus 4 meters per second. And you should note here that your change in momentum is going to be negative due to these negative signs, but it actually doesn't matter because we've been asked to find the magnitude of momentum. So you'll notice that I've dropped the negative sign from the 6 meters per second you see here. Okay, so my change in momentum then will be 3 kilogram meters per second. Next, The ball stayed in contact with the floor for 0.15 seconds. What average force did the floor exert on the ball? So from your data books, you will find that we have this convenient equation. Change in momentum is equal to force times change in time. And from that, we can find the force of our collision. And it is defined here, where the force of the collision is equal to change in momentum divided by change in time. Now, the rookie mistake here would be to just plug in values into this equation and then give that as your answer. And on paper 1 questions, examiners will predict that you will do this because they are devious. Ladies and gentlemen. So don't make this rookie mistake. We need to include gravitational force in our total force. So our normal force then is going to be equal to weight plus the force of the collision. Okay, so normal force then is equal to negative mass times gravitational acceleration plus the force of the collision. Okay, our negative signs are going to cancel out because we have a negative sign in front of negative mg, and g itself is negative 9.8 meters per second. So that is why this has become a positive value. And we plug in all our values, and what we find is that we have a larger force than simple gravitational force. And this should intuitively make sense. So if you're not sure if you're making if you're doing the right thing with your negative sign, just use your intuition, guys and girls, if any are watching. Use your intuition, okay? We expect that force should be larger, okay? So if it's not, then you've misplaced a negative sign. Don't do that. Okay, so our answer then is 25 newtons, and it's fairly straightforward. The only thing tricky about this is the initial setup, and it just takes a little practice. Okay, 2.48. Consider the graph of figure 2.78, which is shown here. The force acts on a body of mass of 3 kilograms, which is initially at rest. Okay, so this is important because it means that our initial velocity is 0. Okay, so and that is important because what we're looking at here is changes in velocity. Okay, so let's look at part A, the initial acceleration of the body. So the initial acceleration of the body will be given by Newton's second law, where force is equal to mass times acceleration. Okay, so initial acceleration then will be equal to our initial force divided by our mass. And we get our initial force just by looking at our graph and noting that initial force here appears to be 12 newtons. Okay, you guys do need to be able to read and interpret graphs. This skill is going to be invaluable over time. Sorry, sip of coffee. Okay, so we plug in 12 newtons divided by 3 kilograms, and we find that our initial acceleration is equal to 4 meters per second squared. Okay, wonderful, very good. Note that we can calculate our acceleration at any point on this chart, and that is potentially useful information. We can also calculate our total momentum at any point on this chart, because the area under the graph is going to give momentum. Okay, so for part B, we are asked to find the speed at 4.0 seconds, and we're going to do that. But first, let's talk about this graph a little bit more. Note that we can calculate here two momentums, what I'm calling P sub 0 and P sub 1. And I don't think we actually need to define them in these terms, P sub 0 as initial and P sub 1 is final, because it's not really working out that way. We're looking here at total momentum over the course of 6 seconds. Okay, so the area under the graph is going to give momentum, as we've already discussed, and that means we have a couple of formulas that are useful here, and basically they're the formulae for triangles, okay? So P sub 0 is going to be given by a triangle, 1/2 force times change in time, and we then take that value for force that we used previously, and we plug it in. And our change in time here is 4 seconds for our first triangle, okay? So we plug our values in and we get 24 kilogram meters per second. Next we have P sub 1, which is the area of the smaller triangle. And here, note that our change in time is 2 seconds, okay? 6 minus 4 equals 2 seconds. So that's important. Okay, the value for force is going to be -6 newtons. Okay, so we plug in those values and we get P sub 2 is equal to 6 kilogram meters per second. Okay, so at 4 seconds, we have a change in velocity, and it's pretty important that we recognize that that's what this is. We have a change in velocity of 8 meters per second. So we've gone from an initial velocity of 0 meters per second to 8 meters per second. And the momentum shown on our chart shows that our change in velocity will be 8 meters per second. Okay, next part. Our change in velocity will be given by our second momentum, the area under the small triangle, divided by mass. So here we have -6 kilogram meters per second divided by 3.0 kilograms, and our change in velocity here is -2 meters per second. Okay, so our total change in velocity then is what we're interested in. That will give our final velocity, and so we add together our two changes in velocity, and we will find that our final velocity is equal to 6.0 meters per second. Probably need to rewrite some of this. It's a little bit messy. Okay, so there is 2.48. Next, we look at 2.49. Ball of mass 0.2 kilograms is moving at 3.6 meters per second on a horizontal floor. And this horizontal floor part of the system is pretty important because if the ball were in air, then the velocity vectors become more complex. We would have to look at horizontal and vertical components of velocity, but we don't have to do that because it's on a horizontal floor. Nice. Okay, so we have an initial velocity and we have a final velocity. Never a bad idea to just define those right off the bat. And we have a time, 12 milliseconds. So determine the maximum force exerted on the ball, assuming that the force depends on time according to figure 2.79. This is very important information. We need this definition because our change in momentum will be given by the area of a triangle once again, okay? And we have to have this information to find maximum force, as you will see. Okay, what we can calculate right away is our change in momentum. And whenever you're working one of these problems, guys, start with what you know you can definitely calculate. So this is very straightforward. We have a change in velocity. We have a change in mass. Note that the only tricky thing here is that we need to establish that our velocities have different directions. Okay, so that is important because it affects the placement of our negative sign. Okay, so the negative sign just indicates that our velocities are in opposite directions. So I have chosen to affix a negative sign to 3.6 meters per second, only because that's going to produce a positive value, and that's it. It doesn't matter. We define the direction of movement, okay? So in this scenario, we would imagine the ball moving toward the left. because the initial velocity is negative. Okay, so our change in velocity then multiplied by our mass will give us a change in momentum of 1.36 kilogram meters per second. Note that our changes in velocity are always larger than individual velocities in the problems that we have solved up to this point. If that's not the case, you are perhaps making a mistake. So just be aware of that. Okay, once we have this value, then we return to our area of a triangle because it will allow us to calculate maximum force. So maximum force can be derived by solving for this value in this equation, and I've skipped that algebra because it's very straightforward, but if you would like me to help you with that, I can certainly do that. Okay, so maximum force is going to be equal to 2 times change in momentum divided by change in time. Note that our time was given in milliseconds, so we need to convert that to actual seconds, and that is what you see here. Okay, we plug in our values and we find that we have 2.3 times 10 to the second newtons. Okay, our last problem, 2.50. This one is a key problem, okay? So you will not be able to solve this without this example, I predict. And if you can, you will have my undying respect, but you probably cannot. So here we have the equation that you need, and this equation is simply based on the conservation of momentum. Okay, so we have initial total momentum equaling final total momentum. And so you can see here the mass of ball 1 times the velocity of ball 1, we're assuming our objects are balls here, is equal to the mass of ball 2 times the velocity of ball 2. And then we have the mass of ball 1 times a different velocity of ball 1. The apostrophe there just indicates that our velocity has changed, okay? So you could consider v sub 1 as initial velocity and v sub 1 prime as final velocity, and that would make perfect sense. Okay, so same for the second velocity. Just a moment. Okay, yes. So, as I was saying, the apostrophes just indicate that our quantities are changed. So we have initial velocity, final velocity. Initial velocity 1, final velocity, initial velocity 2, final velocity 2. Okay, so we use this equation here for non-sticky collisions, or elastic collisions. These are called elastic collisions. But when the objects stick together, our final velocities are going to be equal to each other because our object has become a single object. So our two objects have become one. They're now stuck together. And because that is the case, our equation also changes slightly because our final mass will just be a total mass. Okay, so here's a total mass of objects 1 and 2, times the final velocity of this new fused object. Okay, so these two equations are very, very important. They're not in your data booklet. No. Oh no. That means you need to memorize them. Okay, flat out. You need to memorize these equations. Okay, our setup for final velocity. Remember, we were asked to calculate the fraction of original kinetic energy that is lost. What does this mean? It means that kinetic energy is not conserved, okay? So that is why we can't use kinetic energy to solve this system, at least not easily, certainly. Okay, momentum is a lot easier. So here's our setup. n sub 1 is going to equal m as defined in the problem. M sub 2 is going to equal 2m as also defined in the problem. And v sub 2 is 0, and that is also defined in the problem. Okay? So it is defined in the problem by this word stationary. Okay, so this tells us that initially our second body is at rest. Okay, so because that is the case, this goes away conveniently. So here I start with my initial equation, and then I substitute the values that we defined over on the left here. Okay. Once those values are substituted, we can solve our equation fairly easily. So our velocity, final velocity, will be equal to 1/3 our initial velocity. So next we need to calculate our final kinetic energy in terms of initial kinetic energy. Okay, there are a couple ways that you could do this, and we will look at those different ways over time. So, but in this case, this is how we're going. So our initial kinetic energy is given by 1/2 mass times velocity sub 1 squared. Our final kinetic energy is given by the final velocity as we determined in our previous step. So we just plug that value in here, where v sub 1 divided by 3 is squared. And maybe I will make that slightly more explicit. There we go. Okay, so that means that you can see the algebra here. That means at the end, after our algebra, we're going to have 1/3 of the initial kinetic energy. Okay, so our final kinetic energy will be equal to 1/3 of the initial kinetic energy. So we then subtract that value from our initial kinetic energy, and we find that in the end we will have 2/3 of the kinetic energy lost. Okay, so that last step is important. And that's it for 2.5. I hope you enjoyed it. Again, these equations super important, and you should practice with other problems. You desperately need to practice with other problems. Okay, that's it for this video. Have a great day, and I will see you soon.